Pickering series. The wavelengths lambda in the Pickering series are given by 1 over lambda equals 1.097 10 to 7 meter inverse multiplied by parentheses 1 over 4 minus 1 over n over 2 squared. N over 2 parentheses squared for n equals 5, 6, 7 and were attributed to hydrogen by some scientists. However, Bohr realized that this was not a hydrogen series, but rather belonged to another element, ionized, so that it has only one electron. Part A. What are the shortest and the longest wavelengths in the Pickering series? And Part B. Which element gives rise to this series and what's the common final state quantum number n sub L for each transition in the series? Okay, so let's write the Pickering series. We have 1 over lambda is equal to 1.097 times 10 to 7 meter inverse 1 over 4 minus 1 over parentheses n over 2 squared, and here n is 5, 6, 7, an integer, etc. So that's our Pickering series. Now if I substitute the smallest possible number for n equals 5, what would I get? For this factor here, 1 over 4 minus 1 over n squared over 4, let's calculate this factor. I would have 1 over 4 minus 1 over n over 2 parentheses squared. This would be equal to 1 over 4 minus 1 over 5 over 2 squared, which is equal to 1 over 4 minus 4 over 25. And this number is 0.09. Okay, so let's repeat this calculation for n is equal to 6. N is equal to 6. So I have the same thing here. The factor in the Pickering series, this is equal to 1 over 4 minus we have 6 over 2 squared, so that's basically 1 over 9. And this gives us 0.14, and we can continue with this calculation for higher order n values. So you can see that this constant multiplied by this number is equal to 1 over lambda. So if this number is increasing, that means 1 over lambda is increasing, lambda is decreasing. So as I go to higher order n's, therefore I will get the maximum possible lambda for the smallest possible n value here. So we will obtain 1 over lambda maximum is equal to 1.097 times 10 to 7 times 0.09. This turns out to be 0.09873 times 10 to 7. And that gives us, for lambda maximum, 1 over this value. So we will have 1 over 0.09873 10 to 7. And if we calculate this number, the maximum value of lambda is 1013 nanometers, which occurs for n is equal to 5. Okay, and since as n increases, this value is increasing, which means lambda is decreasing. So we will have the minimum value for n equals infinity. We will have 1 over lambda minimum is equal to, so if this is infinity, this is going to become 0. So it's 1.097 10 to 7 divided by 4. So this will give us lambda minimum is equal to 364.6 nanometers for n is infinite. So we calculated the maximum and minimum wavelengths in the Pickering series. Now, which element is this and what's the common final state quantum number? So let's recall, according to Bohr model, we have the following result. According to Bohr model, the energy levels are given by minus atomic number Z squared, 13.6 electron volts, divided by n squared, where n is an integer, and Z is equal to 1 for hydrogen. So we have this result here. And when the energy, if you look at the n equals infinity level, this is corresponding to 0 electron volts. That means the transition from n equals infinity to the final quantum state n sub L is going to be 0 plus Z squared 13.6 divided by final quantum number square, and this is equal to Hc divided by lambda minimum. Okay, so 1243 electron volts nanometers divided by 364.6 nanometers. This gives us 3.41 electron volts for the delta E corresponding to this transition. Okay, now if I look at the value Z squared divided by n sub L squared, this is going to correspond to, from this expression here, Z squared over NL squared is 3.41 divided by 13.6. 3.41 divided by 13.6. This is equal to 0.25. So let's try what happens if the final quantum state is 1 and L is 1. That means z squared is equal to 0.25. While this is not possible, atomic number z is an integer. So that cannot be. If the final quantum state is 2, z squared is equal to 1, z is equal to 1, that's hydrogen, but we know it's not hydrogen because the hydrogen series looks different. So what if the final quantum number is 3? Then you will have z squared is equal to 9 times 0.25, which is not going to give us an integer either. What if it's 4? If it's 4, then you will have z squared is equal to 4, because 16 multiplied by 0.25 is 4, which means z is equal to 2, which means it's helium. So we find that the final quantum number should be 4, and this is corresponding to helium. Now let's check for lambda max. The energy of the n equals 5 level is minus 4 times 13.6 eV divided by 25, and the energy of n equals 4 level is minus 4 times 13.6 divided by 16, and this gives us minus 2.176 electron volts. This gives us minus 3.4 electron volts. The transition for n equals 5 to n equals 4 is E5 minus E4 energy difference. That is 3.4 minus 2.176. That's 1.224 electron volts. And this is equal to Hc over lambda max. So that's equal to now we know that lambda max should be 1013 nanometers. So let's calculate Hc over lambda max for 1013 nanometers. 1243 electron volts nanometers divided by 1013 nanometers, and this gives us 1.227 electron volts. So these are basically very close. So I realized that lambda max indeed occurs for n equals 5 to n equals 4 transition. So the final state quantum number should be, final level should be n equals 4. It must be helium, and if I do the calculation according to Bohr model, I do realize that the lambda max I calculated in part A corresponds to n equals 5 to n equals 4 transition. So in this problem, we talked about the Pickering series, a series observed for quite some time and was attributed to hydrogen, but Bohr realized it wasn't hydrogen, but rather it's another element ionized so that it has only one electron. And for the series, when we substitute the smallest possible value of n, we obtain the largest possible wavelength, as you can see explicitly here. As n increases, 1 over lambda is increasing, which means lambda is decreasing. So maximum lambda is 1013 nanometers for n equals 5, and the minimum occurs for the largest possible value of n, where n goes to infinity, 364.6 nanometers. The energy levels in Bohr model are given by minus z squared 13.6 eV over n squared, where z is equal to 1 for hydrogen, the atomic number. For n equals infinity to n equals final quantum number n sub L transition, we have z squared 13.6 over nl squared, that's hc over lambda minimum, 3.41 electron volts. So we can isolate z squared over nl squared, and let's check. NL equals 1 gives not an integer z value, so not possible. 2 gives hydrogen, but we know it's not hydrogen. 3 not integer. And 4 gives z is equal to 2, which corresponds to helium. And if we check for the maximum wavelength, on the other hand, n equals 5 to n equals 4 transition, energy difference does indeed correspond to hc over lambda max. For the lambda max we calculated in part A, so the final quantum number should be 4. So the final state quantum number is 4, and this must belong to helium because z is equal to 2.